Not yet.
Wait. Now it is visible?
Yes, yes.
Yes. Shall I start?
Ma'am, let me
Wait,
start.
ma'am.
Let me
Okay.
start the
Wait
recording.
for a
Wait,
while.
wait, ma'am.
Recording is yet
Yes.
to start.
Yes, ma'am. Yes.
Ma'am, you can start now.
Okay. Thank you, ma'am. A very warm and pleasant evening to one and all present here. We welcome you all to our 13th session of 6 days online ATAL FDP. That is Future Trends in Computing, What's Next for HPC and Quantum Technologies. I, Professor Sampada Lokhande, on behalf of AC Patil College of Engineering, Khargar, welcomes Mr. Samrit Kumar Metti sir to the ATAL FDP on Next Generations Computing, Advances in HPC and Quantum Technologies for Data-Driven Insight. Without further ado, allow me to introduce Mr. Samrit Kumar Metti sir. Is a Joint Director, Scientist E at HPC Technology CDAC Pune and has been with the organization since 2006. As a part of National Supercomputing Mission (NSM), he is involved in porting, benchmarking, and technical support of scientific applications with his expertise on high performance computing. Deep learning, machine learning, parallel distributed computing, and accelerated computing. He leads the team responsible for implementing, executing, and supporting deep learning application stack on supercomputing systems under NSA. He leads the team developing Param's Shavak products and AI application stack on supercomputers. Currently, he is leading project on quantum simulator project on HPC system. His expertise includes high performance computing, distributed deep learning, machine learning, heterogeneous computing, accelerator programming, grid computing, system administrations, and big data. We welcome you, sir. Please accept our virtual token of respect.
Thank you very much.
Thank you. Now I request Mr. Samrit Kumar Metti, sir, to start the session. Over to you, sir.
Very good evening to all. I hope I am clearly audible to all of you.
Yes, it is audible, sir.
Okay,
Yes, sir.
let me share the screen. So, is it in presentation mode now? My PPT?
Yes, visible,
Yes,
sir.
sir.
Okay. Good evening, all, one more time. And thank you very much for inviting me, for giving me this opportunity to present the thoughts about future trends in computing. This is one of my favorite topic because I've been working on to various technologies for last decade, and in Syria we got the opportunity to explore cutting edge technologies, say it, supercomputing technology, hybrid computing technology, and we also explored big data technology, and then currently quantum computing. So I think I am in positions to give you informations about it. I'm not a hardcore scientist, so to say, as my profile says, because it's just a positions that my organizations has assigned to me. So rather than I would label myself as a person who is learning technology and who loves to talk about it, inform people about what is next coming up, and how to adopt those technological evolutions and their associated challenges or how to overcome them. So this is a good opportunity, and to express what I think is coming up in future. However, I would be very free and frank to accept the opposite conflicting views from any of or any one of you, because I also understand there is a scope of rethinking, there is a scope of reassessing the way I am presenting and the way you think. So this is going to be an interactive session, and I would really love that if some of you would like to discuss some of the topics that I'm going to discuss in future slides. However, the topic that I'm going to discuss, apart from that, for last few sessions, I think for this is the sixth day of ATAL FDP. So there would be a lot of other sessions that has already been discussed, covered, and many of my colleagues, Dr. Gurmohan, Dr. Sri Amit Saxena, Dr. Vamshi just now presented hybrid computing technologies, and then my colleague Shashank, they have presented about quantum computing. Also, my colleague and dear friend Mandar has presented HPC technology related discussions and presentations here. So, considering that a very detailed, in-depth background of all those scenarios and technological scenarios being covered, I would also take this opportunity that if you have any questions, queries that you think you would like to ask me, I would be very much honored and glad to answer as per my understanding. So if you think that there is something that has not been answered or something that you have not understood or would like to discuss a little bit more, I'd be really glad to discuss that point by any chance. Today, I think in the keynote talk, what I was talking about in the context of Atal MTP topic, and I was talking about how HPC and artificial intelligence is converging. And in fact, this particular phenomena, convergence of HPC and AI, is happening right now. So it's not a upcoming phenomena. People are working on it, and in fact, I have talked about it that the recent Nobel Prize has been given to some of these core research areas where the main computing field belongs to HPC and AI. So this is a very good time, frankly speaking, to explore technology like high performance computing, parallel computing, distributed computing, as well as quantum technologies and AI. So if you are a researcher and or if you are a student who are looking forward to topics, research areas, these are the areas where you may find a suitable match. All right, with this prelude, I would like to begin my session. So I was actually thinking about that. How do I present what is upcoming? Then this is how I have planned my lecture. I'll be giving you the platform and compute infra outlook. So I think in a last session, Dr. Ramsey has discussed about how hybrid computing is shaping the world of computations, and how hybrid computing is also a reality today. So in fact, the most valuable company, NVIDIA, they are the prominent player in hybrid computing. I remember my days in 2006 and 7, somewhere between 2006 and 7, when I started working on computing unified device architecture, that's called CUDA, which I am sure that Dr. Vamsi has in detail, in depth, has explained to you. So this compute unified device architecture related um, programming paradigms were coming up for the first time in the world. Well, before that, there were many other programming paradigms like CTL, close to metal, CTM. Then there was a programming paradigm called Shell. It is not a programming language, rather it's a programming paradigm, which means that a programming style in associations with a library middleware support is availing a computational infrastructures to the generic computational scientist people. So this is what the programming paradigms actually mean, which means that it is availing or it is making it available to the end users for the first time. So Cell SH it is called actually SADA programming, CTM, and then Brook and Brook Plus were some of those new programming paradigms were coming up. And in fact, Brook and Brook Plus, if you look into, they were ancestors of CUDA and very very powerful. I mean, they were not that generic, a little bit restricted programming style, but yeah, they were very powerful. And when I was exploring those technologies and language paradigms, I was very amazed to see that what the level of possibilities it may bring in future. It was very difficult time also for the programmers because of the fact that CUDA was not that easy to program. I mean, the graphics card that were coming into the market had very limited capacities, and the restricted programming style, restricted programming approaches was limiting its possibilities and as well as the client base, the user base. So people were very hesitant to take up what future has as a huge prospects. So a lot of the people has criticism saying that whether CUDA would be very popular or not. And today I'm standing on 2024 and I'm talking about 2006. You know, when I look back to those time, I remember that how people were critical about adopting CUDA, OpenACC, etc. And then today I see that a company like NVIDIA is becoming the most valuable company in the world. And this is only possible because the reason that NVIDIA as a company has kept in, they have invested a lot into behind this. There were other programming styles like OpenCL, and they are open source. So other companies like Intel and NVIDIA were Intel and AMD were investing a lot behind them, and OpenCL is also a very good programming paradigms, quite a powerful with respect to CUDA. But yeah, it is little bit more difficult to program than CUDA. So I'm just connecting those time. I remember my manager was very very optimistic about CUDA programming, and he was one of the first proliferators of accelerator programming that time. I also saw that a lot of criticisms from other friends, his own colleagues, and they were saying that it's too difficult to program and it won't be that popular and this way and that way. But I could see that he was able to envision and he was able to understand the possibilities, the computational capacity possibilities that CUDA is bringing in onto the plate under the scenario of high performance computing. So this is the early days of um, graphics computation, generic graphics computation days. And then I saw the complete evolutions and evolutions of this hybrid computing domain. And today, very confidently, I can say that it is one of the most um, powerful programming evolutions that happened in recent time. And that is giving me a confidence to talk about what is going to be in future. And if I have to present you the future perspective, it is my responsibility to also give you a sneak peek into the past. And I must also make you aware about how the computational infrastructures, their approaches, their designs are almost same. It is just a different outlook they take with the time, and that is how the revolution comes. So if I look back into the traditional high performance computing and then evolving natures of grid computing, cloud computing, you remember in 2010, the grid computing, apart from grid computing, cloud computing was coming up slowly and it was picking up. People were started talking about it, and then grid computing slowly vanished and cloud computing picked up. And today, cloud computing is one of the most powerful programming technique, computational platforms, and it is making the whole world capable of accessing the computational facilities, large scale computational facilities on their through their laptop. It's basically, I may say, if you allow me, that's the computational facility at your fingertips because of cloud computing. Then the big data revolutions came in 2000. 12 time. And at the same time, I must inform you here that at the same time, a revolutionary paper came up in image processing, and almost at the same time, 2013 and 2014 time, ImageNet, ImageNet, the ImageNet related competitions came up, and that created a huge buzz, a very strong momentum. It actually infused into artificial intelligence, deep learning, and today everybody is talking about it. So 2013 and 2024, so a lot of things has happened in between, and the kind of revolutions that are happening around AI and DL is unbelievable, and it is bringing up so much of disruptions into the world. We don't know how the world is going to look like after 10 years. Even we also don't know how our next generations is going to use the computations, uh, how they are going to use the computer science as a subject. What are they going to learn? We have very little idea of. But yes, the if I sit and think, analyze the past, possibly there is a little bit directions towards the future, and that gives me the confidence to talk about the future. And I would take you through the journey of um, from, let's say, 2000, maybe 1990s traditional high performance computing, and then starting from there to current time, and little bit of futuristic approach, futuristic things, technologies that's currently happening in my company as well as around the world. So once again, I really appreciate that if you have any questions, you may please go on asking them, interrupting me anytime. All right. So when I introspect into the past, I see that traditional high performance computing and the grid computing and big data technologies, certainly people are talking about them a little bit less. So people about traditional high performance computing, when I say, let's call it HPC, this is there from 1980s, I would say, even prior to that time. The investments, big superpowers like America and European states, they did a lot of investment there. In 2010, you won't believe, in 2010 there were very few number of HPC systems on a list called Top 500. The list is called Top 500. I am sure that somebody has talked about it. Now, this Top 500 is actually the list of supercomputers around the world. Top 500 supercomputers around the world. All right. In 2010, there were a very limited number of, if I'm not wrong, there were almost 10 or 12 number of supercomputers from China on that particular list, and they were nowhere close to the top category. And today, you won't believe, they they actually having the fair share of almost 30% of supercomputers, number of supercomputers, top supercomputers around the world on the top 500 list, because they realized in the last few decades that if they have to scientifically move to the horizon beyond and explore into unexplored domain of science, they require supercomputing capacities. If they don't have it, they won't be able to compete with other superpowers. And they have invested into everything of supercomputing component. And today I will actually explore a little bit of that. They have invested into everything, building the processor, building this accelerator computing field, building their own applications, building their own systems, whatnot. And within 10 years, today, if I say, they are almost having 30% share in the top 500 list, and that too in the top categories. In fact, 3 years back, they had Tianhe systems, which was the most powerful supercomputing systems. Today, I think it is Tianhe 2, which is also one of the most powerful supercomputing systems in the world. Well, so supercomputing investment into behind the supercomputing systems, every country every advanced countries does a lot because they understand the significance of it. So in 2000 time, the early days of supercomputing were also very limited capacities. So the applications were very powerful and they demanded very high computations power, but the computational facilities were not in positions to give them because it required humongous amount of investment from the government itself, and also as it is science, so there is a lot of chances, uh, high degree of chances of failures as well. That means the outcome, the tangible outcomes were not connected to the societal impact, which means that you may do a great science, but possibly it will not directly impact the society. You understand my point, right? Today, if you see in comparison, AI, in earlier days, AI was a research field. Today, AI has become a technology which is directly impacting our world, our day to day life. So, supercomputing is not of that category, and were not of that category during those days. So, many of the governments has little bit hesitations that whether to invest behind it or not. But superpowers, and they have a lot of money, as you know. So they understood that, and they have invested a lot behind it, and that is why they are only in the top categories of top 500. So, but as the system were limited, they thought of how to overcome of that challenge, and they thought of something called grid computing. And I will explain why grid computing was a humongous supercomputing concept. Distributed supercomputers at different locations across the continent were supposed to be connected. I'm saying supposed to be connected because that was the reason behind grid computing. Were supposed to be connected and their computational facilities to be explored. That was the thought process behind grid computing, and how it is going to work. I will explain a little bit about it. When people started working on grid computing by 2005, the researchers realized that it's too complex, and it's in fact, early in my career in 2006, I worked on building a grid computing testing software suite, and that package, development of that package was a challenge. But apart from that, maintenance of a running grid, where all the component of a grid computer were a very heavy challenge. And on those days, the network bandwidth between different locations, geographic locations, was very limited. So eventually, people started to realize, okay, we have to move to some other technology, or maybe some other kind of a technology is supposed to be used instead of grid computing. Then people started to explore something called cloud computing, which is an extension of service oriented architecture. And however, it is an offshoot or offspring of grid computing. So what I'm simply saying that they were related. They are not cloud computing actually did not came out of grid computing, but we can consider them. They actually had a lot of similarities that way. And then into 2008, 9, 10, 11, and 12, rather. During that time, a lot of big data related discussions happened, technologies development happened around, and then we also did a lot of hybrid computing, which is accelerated programming. And lately, nowadays, we have been talking about neuromorphic computing. I'll talk about why neuromorphic computing is also becoming very interesting stuff to work upon. Apart from neuromorphic computing, there is another topic which I also touch upon, and that is called uh, specific AI specific or AI oriented computational architecture. There are a lot of systems that are coming up, that are coming up just to facilitate just to facilitate AI and deep learning related computational requirement. Cerebras, you must have heard name of, called Cerebras computation system. I'm going to talk about it. And at last, quantum computing. Quantum computing has a very interesting case studies. So what happened in a traditional HPC system, there are a lot of applications which does simulations of a real world phenomena. We call it scientific computing. So those scientific computational simulations are basically done using a linear algebra mathematics. All right. However, at core, in reality, those simulations are basically stage-wise form in stage-wise form. But what they are simulating on, they're simulating a real-world phenomena, and real-world phenomena of such categories are quantum in nature. So what we are trying to do then through scientific computing, traditional scientific computing, a quantum phenomena is getting simulated through a computer science and linear algebra on using quantum using scientific simulation technology. So which is based on digital logics, etc. So this is a very naive, brute, and slow process, and not so good approach of simulating a real world phenomenon. But that is what the whole world is doing currently. Even all of the HPC applications, if you consider, they are doing the same thing. That is the exact thing they are doing using supercomputers. Because we don't have any other breakthrough as of now in the computational field. But yes, um, right now, because of quantum computing, we are observing the possibilities of a breakthrough. What kind of breakthrough? There is a possibility that a quantum phenomena could be simulated through quantum computing. And if it is done, you understand that there will be a traditional calculation part and there is a quantum computational part. So quantum computational part would be handled by quantum computing, whereas the traditional computing part of that applications would be handled by HPC system. So if if we are able to connect an HPC systems with a quantum computing systems, and if you are able to properly code and run and scientific simulations applications of that level and of that category, will have humongous uh, efficiency, performance benefit, and power efficiency. So now power efficiency, why so? Because supercomputers consume a lot of power, hell lot of power. Okay, so in fact, the most powerful supercomputer of the world right now may consume almost up to the total power that is consumed by Pune city, and that means Pune city consumes whatever level of power a single supercomputing facility would consume that level of power. So the government is very much concerned about this power consuming nature of the supercomputing, traditional supercomputing facilities. They wanted to explore and understand whether there is an alternative. And science has always gone into, explore the new horizons in order to understand whether there is new possibilities to optimize things. Optimizations of all kind, performance optimizations, power optimizations, bandwidth optimizations, this is that. So science has always done that. They have discovered new techniques always to do things in a better way. That is what science does in most cases. Quantum computing is providing and showing the possibilities of that kind. So people are very much excited. You must have heard that Willow recent announcement from Google, their quantum computing systems. I don't remember exactly that quantatrillion. I think number of if you wanted to do that calculations on a traditional systems, it's like quadrillion number of years would take that particular calculation, whereas quantum computing is doing it under 30 seconds. That is what the current uh, news and which is circulating world around. And we are also very much excited. The possibilities and chances are there, but things are not that straightforward, frankly speaking. I would explore and discuss a little bit of that. Well, so this is what a brief introductions, or rather a detailed introductions of what I'm going to go through fast. Before I delve into the next slides, do you have any questions at this point of a time? I will take quickly and then move forward. Any questions? Okay, fair enough. So, am I audible clearly? Can someone confirm?
Yes, sir.
Yes.
All right, all right, good enough. So all set. So with these particular introductions, let me move forward. I think this particular sections of slides I have gone through, but I want to give a recap. If somebody is new, let us give them a brief so that we'll all be on same platforms before we move forward. What HPC facilities is, a supercomputing facilities is basically practice of aggregating computing power, that is multiple nodes you aggregate together and build a supercomputing systems where a middleware of that uh, facility, which is a collection of libraries, operating systems, network libraries, communications libraries, programming middleware, etc. All of them creates a middleware, HPC middleware. They basically tied and glue together all these different compute nodes, and once when you go into using them, you feel like you are working on a single system, and you take benefit of high computing power. That is what high performance systems is. So yesterday's high performance system is not today's high performance systems, and today's high performance systems would not remain a high performance systems of tomorrow. And this is an evolving fact. We have to accept this. 20 years back, what we called as a HPC systems like around 10,000, now your mobile have that compute capacity. You won't believe this, right? So 1 gigaflop of compute capacities, around 10,000. So this compute facility is nowadays in your pocket, and tomorrow what is there you don't know. So these kind of radical changes are coming up in computational field also in performance perspective, and that is why we say it's always changing. It's never stable, and it is always also falling short of expectations. Whatever level of computational power you give to the scientists, they will explore the beyond of it, and they will tomorrow come back and say, no, no, I want more number of compute capacities. So can you provide me that? Because when a science or a domain scientist explore and develop a mathematical theorem, they develop a generic theorem. Now, a computational facility is not a generic facility. So it's a limited facilities. They have limited number of nodes, limited number of cores. Whereas a mathematical theorem is a generic one. Today you apply the mathematical theorem and develop a program with certain boundary conditions. Tomorrow you may change the boundary condition itself, and that will demand humongous high level of computational power. And that is why the domain scientists are very good at keeping us on toes all the time. The people who are on the computational and infrastructure sides, people like us. So they always very quickly come back and say, no, no, this facility is not enough. We require higher facility. So that is why we never develop a standard definitions of it. And we always consider this yesterday's supercomputing facility is not today's supercomputing facility anymore. And the same thing is going to happen with today's supercomputing facilities in tomorrow. I have talked about it in 2013 and 2024. Nobel Prize were directly given to development of scientific simulations applications. And frankly speaking, in future, you would see many more number of explorations been awarded Nobel Prize where there is a touch of high performance computing, artificial intelligence, and maybe quantum computing as well. So we have to just be more watchful about it, and a lot of interesting things are going to happen, and many more people will be talking about HPC, AI, and quantum computing in future. Recently, I was discussing with one of my friend, and I said, see, in earlier days also there was not much talk around HPC. People know little bit about them, and very less awareness about HPC were there. And today, a company like Nvidia has complete talking on AI and quantum computing. They are not talking about HPC. The person replied, he is also a lover of HPC field, so he belongs from that field. And he also talks are very important. He answered me that whatever they does, there is HPC touch always in the background, and that is why, as it is in the background, you possibly don't know about them, but they are there. So that is what the interesting part of HPC. HPC has always been there into scientific explorations by the domain scientists. They are day-to-day basis used. However, very less number of computer science people, engineers knows about them, and because of obvious reason, there are less number of facilities. I'm sure that some people has talked about National Supercomputing Mission (NSL), and this National Supercomputing Mission is for that purpose only to bring awareness, to create lot many systems around the country. In fact, at this point of a time, if I'm not wrong, more than 16 or 17, even more than 20. I exactly don't remember the number. That many number of facilities been installed across premier institutes, IITs, NITs, IISc, ISR. So at many places, premier institutes, and lot many scientific uh, fraternities are exploring using those facilities. Why they use them? That is the question we have to understand. Why they are so much interested about HPC, where they are just scientific, they are the scientists, hardcore scientists. Why they use them? So if you look at, in today's world, lab experimentations by using instruments are very costly affairs, and that is why it is less. It is to be done at the last stage, not less preferred, but it has to be done at the last stage. Before that, whether we have any chances to find out prospective candidates for explorations. Let's say I want to explore some molecules. So there are 20,000 molecules, and I want to develop a vaccine by combining those molecules together, uh, which falls under drug discovery. Now it is very challenging field, development of vaccine in earlier days it used to take more than 10 years, like 17 years, sometime 18 years, the trial testing and everything. But the major part of the cost used to go into the lab testing because they used to do in physical form in the lab, in the wet lab we call. Nowadays, what is more preferred is dry lab experimentations. We have softwares. In fact, I'm talking about the software which has been awarded Nobel in 2013. Okay, molecular discovery, molecular combinations discovery applications. It's called molecular simulations, MD simulations applications. Okay, so what it does, if you have a base molecule and attach another molecules into that particular solution, how they are going to interact with each other and come to minimum energy state. Now, you must keep this particular phrase in your mind till the last of my presentation. What is that? Minimum energy states. And this is a natural phenomena. In all cases, nature has the tendencies and has the preference to go to minimum energy states. Okay, this is nature preferred, and that is how the bond between the molecules are developed. The more minimum energy states the molecule is, the bond between the molecules are that higher, or vice versa. All right, and that is why when a new material has to be discovered, if a very strong material has to be discovered, we have, they try to find out how the bond energies been calculated and whether there is a minimum bond energies we can discover just by simulations, because doing that kind of explorations in a lab physically is very expensive again. So that is why they perform lot of simulations. Now how the simulations will be performed, technology can be of different types. All right, it can be artificial intelligence, it can be scientific simulations, etc and etc. But that is basically abstract level of technology. Computational platforms remain same, HPC facilities or cloud computing facilities. So that is how the simulations takes place. And on the other hand, you have theoretical model, which you construct approximate theories. Once you do the simulation, you matches your simulated output with theoretical predictions and compare it. So this is one output or one kind of a prediction has been done. The other kind of prediction is also very important. What is that? You do real lab testing here, and you get the experimental results, and then you match your results with scientific simulations. In both cases, you see, scientific simulations is a common field. So once you do this, then you compare it. And once you compare it, you have a very strong case where something and where your experiment, real world experiment is saying something. And this gives the most possible right candidate of a molecule for the drug discovery point of view. And that is why it is being practiced by all the drug companies. The major drug companies you see around the world, their scientists uses HPC facilities on day-to-day basis. In fact, there are many other cases where HPC facilities, including stock market predictions, that are there. So that means, as I said, you may not know that supercomputing facilities is in use, but they are there in many of the cases. I have talked about it. It is WRF applications modeling scenario. I have explained in my keynote talk, and I'll go through very fast here. What we do simply here is dividing the domain into subdomains, and each of the subdomains are basically collections of parameters. All those parameters interact with side by subdomains parameters. That is how the interactions between subdomains happens. Once you see this collection of a parameter as a structure, so that means they are basically a point which is interacting with other points, and that is what happens here. So this is how the simulations actually it starts. Um, is there any question, please? Okay, so that is how it starts. So it is basically the interactions between the data points. Once they are being they have been modeled as a data points after dividing a domain into subdomains. Their interactions, stage-wise interactions over the time, gives the predictions final output. How the tornado or any other weather phenomena is going to take place, what is going to be their final form after a certain point of a time. All these things are basically a scientific simulation step. So the domain decompositions into this whole process is a very crucial stage. The domain is so big in many of the cases. In case of drug discovery, molecular simulations also, the domain or the systems is so big and the number of the parameters is so high, the number of the calculations is so high that you can't do it on your laptop or high-end server also. You have to decompose them into subdomains and then give it to different systems. The simulations talks about it. This is the domain decompositions simulations of that. Once the data is prepared, the domain has been decomposed, you distribute it. Subdomain to slave nodes. When I say slave nodes, it's basically the compute nodes I mean to say. And the master nodes is responsible for coordinations. That is what a mapping of scientific simulations process to a physical computational process. And into all of this, the storage is a very important part of it. The storage here, though it is connected through the switch, but logically, storage is available to all compute nodes as well as the master nodes. I'll give you another picture of that so that you can understand how an architecture and organizations of a supercomputer is. So this particular storage, which is network mounted NFS, network file systems it is, and there are many other file systems also. Lastar is one of the most powerful parallel file systems. So these file systems is available to all compute nodes. So when master nodes distribute the computational responsibilities to different compute nodes, all right. Now the responsibility of the compute nodes to access the domain-wise data from the storage, because these compute nodes, though the storage is located somewhere and it has to be accessed through network, the compute node, as it is mounted, as this storage is mounted on this compute node, the compute node feels the storage is its own. All right. So all the compute nodes thinks that this particular storage is my own storage, and they act that like that. They directly access. However, there are penalties. The penalties of accessing the data from here is very high. And in optimizations domain, the domain that I work in, performance optimization, there it is a very important factor. So we do a lot of FO programming techniques, do apply them into day-to-day basis programming development as well as executions of applications. During the executions of the applications, and those optimizations techniques helps us to minimize the storage access penalties, and that is how performance optimizations works. Anyway, so the responsibilities of computations been assigned here, compute node, and then the compute node responsibility is to complete that task. Once the task is done or completed, it will revert back to the master node telling it that okay, I have done my part and here is the result. So that is how the whole scientific simulations in a brief, very easy to understand, but well, when you go on practicing them on day-to-day basis, by any chance, by any time, if your organizations or you yourself build a cluster system, supercomputing cluster systems with let's say 4 node or so, then you would understand how difficult or how challenging it is. But it is very interesting. Once you stabilize the whole facility, the supercomputing facility, it will remain stable for very long time. So that is why a very strong system admin team is always behind of this kind of infrastructure. And this is true for cloud computing also. For general programmers, computer science people, engineers, domain scientists, they don't realize the challenges, nitty-gritties of this infrastructural part of it. But yes, they are there. So if I go by the component, there is a head node, there is a login node. And why there is a different thing, login node and head node? This is a shared facility. That means at a point of a time, more than 200, sometimes 1,000 people are accessing the complete facility. So if there is a single node which is used for SSH, secure login, secure cell access, by thousands of users at a point of a time, the node itself will fail. So there is a mechanism of load balancing on the login node, which is done by the head node also. So there will be actually multiple login nodes, and all these login nodes is giving a gateway to access to the head node. In most cases, head node and root node are same, but in many cases, for big facilities, the root nodes and head nodes are also different. So what this root node does, root node basically responsible for managing the facilities and keeping all the services alive, be it file system service, be it network service, be it operating system services, etc. and etc., be it scheduling services, etc. So all those root nodes responsibilities that, and that is why there will be a backup root node as well. One root node fails, the other root node would take over. Head node is also of similar kind, but here when I say head node, it is basically once you log in onto this login node, you jump onto head node, and this happens in a transparent manner. You won't basically realize once you do the SSH, you won't basically realize that you have been dropped from here to here. Automatic forwarding is there. So you will basically be dropped to the head node place. Now, head node also responsible for managing the complete infrastructures in tightly coupled manner by using or with the help of middleware. What is there in the middleware? In the middleware, there is a process manager, scheduler, a middleware set of softwares, set of applications, and monitoring tools. All these in a combined, we call the supercomputing middleware. So this is how the whole facility works. And when I say the distributions of the work, the distributions of the work or an applications happens from here to the compute node. This one is a storage server, which is also through the network is connected to all the compute nodes for the computational purpose. Now, if we look into this is a single slide picture of lot of scientific kernels, which tells us and gives us a map that basically these two type of basic geometry applications and um, basic um, basic matrix primitives. Okay, there this is the two basic categories, and there are so many different type of solvers. Okay, Cholesky solvers, basic iterative solvers, Jacobi methods, etc., eigenvalues calculations, calculation libraries, etc. So all these different techniques and algorithms, they are packed into different category of libraries, which falls into two basic broad category: basic matrix primitives and basic geometric primitives. If you look back, bottom up approach, they map up to different domains: computer vision, rendering, physical simulations, financial analysis, data mining, artificial intelligence, etc., etc. The list is so long. So in all cases, you will be basically using a middleware layer libraries. Okay, those libraries would allow you to program and develop your applications for on a supercomputer. And the important part of is you must know the parallel programming also, because you see, though it is looked as a single block, they would be basically utilizing multiple compute nodes for the calculation purpose. So they needs to decompose the data to different nodes before the calculation happens, and then once the calculation is done, they needs to correct the data back. So it is kind of a scatter and gather kind of an operations happens here. And that is why all these libraries, when I mean to say, they are not a single systems libraries. They are parallel libraries. They are distributed libraries. They can, once you develop a program based on these libraries, they can distribute the work to multiple nodes very efficiently. And that is why it is very important that you learn parallel programming before programming a supercomputer. So parallel programming is a very important part of learning, the whole learning in
Mm.
under HPC. Yes. Is there any question, please? Okay. So parallel programming is a very important part of it. C, CPP, Fortran, Python, Julia are the major programming paradigms and programming technologies, programming languages. They are used for parallel programming. I will name them again: C, CPP, Fortran. Fortran is a major programming language in parallel computing domain. Fortran, um, Python, Julia. These are prominent players in parallel programming. Uh, I would request, yeah, okay. Thank you. So this is what the programming techniques. There are many other advanced additional programming techniques are available, like Complete Unified Device Architecture, CUDA programming, OpenShell programming. For parallel systems, like a supercomputer, you have OpenMP, MPI, Message Passing Interface, pthreads, IntelliDB, and many more. These are programming paradigms. They are not programming languages. CCPP are the languages. These are all programming paradigms. So basically, you can program or apply these techniques using languages like Julia, C, CPP, and Python as well. But what you program upon, that also you need to keep in. The computer architectures, that's there is a variety of it on a supercomputing platform itself. CPU, GPU, and accelerators. When I say GPUs and accelerators, there could be many other kind of accelerators. Intel Xeon Phi is one of them. FPGA, cell broadband engine. These are another set of accelerators apart from NVIDIA GPUs and AMD GPUs. In earlier days, we did a lot of programming on Intel GNP in 2013, 2010 to 2013. A lot of programming. In fact, Param Yuba, the first version of it, were based on Intel GNP accelerator. Now it has been discarded by Intel. It was from Intel. So apart from a CPU programming, for the parallel programming purpose, you need to know the architecture of all this. And that is how will make you enable to program a supercomputer for any of the technologies that you want. I was talking about the grid computing. So when the scientists thought of, okay, these developments are happening around, but I want more accumulated computational power. How do I do that? And they came up an idea of grid computing, which is basically understanding of aggregating geographically distributed computing cluster. So on a supercomputer facility, if I say, they are basically located at the same place. Let me give you, so this compute facility would be located at the same place. Either it is an same locations and very tightly binded, though over the network, but they are very closely located, closely placed. possibly in the same room or in the same facility. But if you want, if there was a vision with grid computing, if you want more compute facilities, why not integrate many such facilities? Those are geographically located at different places, and then program them. That is the concept behind grid computing. You see, some cluster, which is a technical term of a supercomputer. So some cluster would be located somewhere in Canada, and some clusters would be located somewhere in Europe, and you know they are connected over internet, or maybe a more dedicated connectivity network. And then once they are connected together, once you place appropriate middleware, which is called grid middleware, you are good to go to program them and consider the two distributed physically located at different continents, but you would be allowed to consider them as a single facility. The way in a supercomputer, multiple compute nodes are aggregated and a supercomputing facility is available to you. Here, multiple supercomputers, connected together, and a grid computer is given to you. That is what the idea behind of it. For that, there are so many technologies. It's a virtual computing resources, humongous or a supercomputer concept, and that is how people were very excited to program a grid computing system. However, when the complete development of grid middleware happening, eventually they got many more ideas, which then got ported into cloud computing later point of a time. Okay, initially it was service oriented architecture. Later point of a time it became cloud computer. You see here you have a portal through which you would be able to access the computing facilities distributed located at different places, geographically located, and monitoring and discovery services is responsible for identifying which computational facility is free relatively, so that your job would be transferred there, or a part of your job will be transferred there. So there is a agent or a broker element, which is again a software element, would be responsible for identifying and sending the request to monitoring and discovery services module. It will tell that where the computation facility is available for you. And all these are supposed to happen to grid security interface, because security is a major part of it, and all these is supposed to happen through these security interfaces. So you cannot bypass this particular layer while you are doing a grid computing. Once it is done, then you will be requesting a scheduler, which is again not a normal HPC scheduler. It's a meta scheduler, and that you will be telling them, okay, here is my job, and then you need to find out almost, let's say, 2,000 compute nodes somewhere. Now, maybe in one European cluster you found 1,000, and one Canadian cluster you found 1,000, rest of the 1,000. So that means you need to divide the task into two different places and offload it to different facilities. Scheduler, which is a meta scheduler, responsible for doing so. And then, as in a supercomputer it happens, you need to now distribute the data, which is falls under the data management part of it. So that means there is a lot of exchange of data between different computational facilities should happen, and computation may start beyond it or parallel to it. So for all these purposes, there are so many important components, like GAAA, Global Access to Storage, and information services of different categories. One is resource information services, another is index information services. Resource information services and index information services are of different category, because index information is basically manage what are the clusters that are available or up and running. Resource information services is responsible to find the resources, compute nodes inside a cluster, etc. So all these components collaborating with each other, providing information to monitoring and discovery services telling to the brokers request that okay, these are the facility available, and you as a end user, then you will be telling the scheduler, okay, pass on the data. Then the data management module will take over, and the data will be distributed, because it may happen that the data is here on this compute node, and you need to transfer into these facilities. In that case, it has to be taken over there. All this is done. Suppose your data has been now placed at proper locations where the competition is supposed to happen, then you initiate the job. That means the job execution should start. So this is also a very normal look after how grid computing works. But in reality, applying them development of the grid computing middleware were very challenging. But frankly speaking, it's still operational in European countries, European continents. Many of them uses them as a not as a computational grid, but many of them uses them as a data grid. Okay, so this is what mostly about grid computations, which is a very powerful computational facility concept. Then I'll talk about a little bit about what India did. India developed a grid called Garuda grid, okay, where multiple cluster at different locations, including a cluster in JNU, a cluster Juba cluster, and that is available in Pune. They were all connected to, and through the grid middleware, grid Garuda middleware, which was actually a Globus 2.04 middleware, that middleware, using those middleware, we were able to program our grid computing systems, and India's own grid computing systems called Garuda. Here is a map where which is showing that how many places were connected for the grid computing project. All of them were through NKN, National Knowledge Network. They were all connected through, and during those time, it was a very high bandwidth connections between the different computing places, computing facilities, and all those facilities were almost distributed across India at various states. So once grid computing moved on to another concept, and then as I was telling, service-oriented architecture took over, and they thought that peer-to-peer computing would be the next generations of computation facilities, and slowly web services and their related technologies evolved into something called cloud computing. Another technology was very crucial into the breakthrough is called virtualizations. So when the virtualizations become very strong and powerful and stable, cloud computing become a de facto standard for distributed computing. All right. So these happen still till the mid of next decade, earlier decade, 2015 up to somewhere around. But in 2010 and 2011 time, another computational technology were coming up. But this is not related to infrastructure facility organizations. It is more of how do you reorganize the computational pattern. How do you reorganize your algorithm? And that is called Hadoop map reduce algorithm. Okay, so this is more of a little bit of abstract level at programming there, or I would say at the middleware there. What Hadoop did, they came up with a concept of distributed data objects. That means you may have a data storage file which has multiple blocks and sub blocks, and each of the sub blocks will have multiple replica of it, and they will be distributed randomly or by following some algorithms will be distributed onto multiple nodes, and then somehow you map your computations or sub computations to those nodes where the data is situated. So instead of in grid computing, I was talking about taking the data from one node to another node. MapReduce took the other approach. They said where the data is, send the computations there only, so that you don't have to transfer the data by yourself. This is a very powerful concept, and that is why it became very powerful for big data computation. Nowadays it's now a de facto. Lot of computations happens. However, the platform is mostly cloud computing platform. For the log processing, for the web indexing, these are the technologies on a day-to-day basis people use. So big data computing or map reduced computing, it's a kind of a fine grained. Why it is fine grained? Because you always divide and subdivide your computational task and map them to computational unit, and then you reduce them. When I say reduce them, it is basically some kind of a aggregations of either subtractions, aggregations by division, aggregations by multiplications, etc. But technically, I would call it as a reduce operations. In parallel programming, this is a very common technique. Initially, you distribute the data, master distributes the data, and then master collects back the data, scatter and gather kind of stuff. Okay, so reducing is a little bit advance of gather. Gather means you simply collect the data and organize, but reducing means there is an operations also attached to it, which means that if you want to reduce a multiple values into a single unit, you need to perform some operations, either addition, subtractions, etc., etc. So these were became very popular at certain point of the time, and you know those kind of a cluster we used to call them as a big data cluster. So here you see you have input files and you split them into subunits, and then you map them. You map them to compute facilities or compute units, to multiple compute units, and they work on different data units. All right, and then at the end, you will be basically by applying some operations, you will be taking a limited number of output. That is what map reduce job does. Intel and IBM came up with a good ecosystems behind MapReduce. They developed a lot of middleware during that time. Currently, also developments are going on for the big data computations, and a lot of database oriented, data oriented, big data oriented tasks still today are executed in MapReduce patterns. And they are very powerful because they have inbuilt replications facility. That means in somewhere in between the computations if fails, okay, they have a logging mechanisms, a log maintaining mechanisms we call journaling mechanism. So they can take back from there. That means if something fails in between, after a certain point of a time, if you want to start, you can start from that milestone. You don't have to start from the beginning, the calculations. That means it saves a lot of time. The second benefit of distributed database is that it also replicates the data. That means if some compute node fails, the data object that it's holding, there must be other compute units who is holding a replica of it, and that gives a lot of confidence for big data companies, because the companies who are completely relying on big data, they don't want to lose the data because data is money for them. So they always wanted to have file systems or a data handling mechanisms which inherently manage the replication process and backup mechanisms. Big data and especially distributed data file objects mechanisms gives them that possibilities. MapReduce is a method or a kind of a programming framework which gives them the power to look into the data, understand the data, and do some operations on data in order to get the final output, which is called reduce operations. So this is also from Intel, and you see, it is little bit different. Okay, the earlier one is a real MapReduce ecosystems where you basically have a lot of virtualized cloud services, but this one is a MapReduce services on a HPC facility. So if you look in this mob, Slum, Luster, HDFS, OpenMPI, they are basically the HPC facility. So we also did a lot of MapReduce operations on HPC facilities, because we also thought that HPC facility can be a good candidate apart from cloud. And right now, even today, a lot of MapReduce related and the big data related calculations, they are quite friendly to HPC facilities. But over the time, uh, their R&D part has reduced. I must confess that here. So it has again fall back to two more prominent areas: scientific simulations and artificial intelligence. MapReduce is slowly reducing, though it is still researched a lot. So I would take a break here for one moment. Is there any questions? Because we are on the last leg of my presentations, another 15 minutes to go, and then I'll conclude. But if you have any quick questions, I may answer that.
Participants, if you have any question, please post it in chat box, or you can unmute yourself and ask your question.
Okay, so this picture basically um, gives an idea that how on a HPC facility a MapReduce ecosystems exists. Lately, another kind of phenomena happening around, that how AI oriented computer architectures can benefit. And what are the benefits they are going to have? The first one is the cost benefit, the second is power efficiency. And when I say AI oriented computer architectures, it means that the way AI applications want the computations to happen, the architecture facilitates that. So we are not looking at a von Neumann architecture, by the way. So a von Neumann architectures where the generic computations happens, AI oriented computer architecture is not that kind of. They are more specific. They are more specific to AI compute type or compute categories. So what happens is artificial intelligence. We all almost know about it. That it is basically a artificial neural network where you have a lot of input parameters, and we can call them weights, and then the weights and input parameters, they basically get operated upon on each others, and then they comes to portions where they amalgamate. Okay, and based on these amalgamations and final situations, the activation happens. So this is what the overall picture of an artificial deep learning. This is a basic building block of a neural network. A neural network would be called as a deep neural network if the number of the layers goes beyond two. And these kind of neural networks, including nowadays a llama LLM models, transformer models, they are very very big, very very deep, lot of parameters. In many cases billion number of parameters are in place in executions, in operations, in a single cycles. So that is why a neuromorphic computing is also a specific area of research coming up lately. Why? Because they thought of that. I'll show you the next picture. At the MOS level, CMOS level, okay. Earlier, the neural network, all these are happening on a generic computational facility. You may think of as a von Neumann architectures. So the von Neumann architecture is fixed. You cannot change the von Neumann architecture. The normal CPU facility is a example of a von Neumann architecture. What you normally do is you change your algorithm or the complete flow graph. You modify the flow graph in order to suit, in order to fit into von Neumann architecture. That is what you do while an AI engineer or while an data scientist does their computations through some framework like PyTorch or TensorFlow. So what these frameworks does, they basically enable you to take benefit of a von Neumann architecture for your deep learning computations. Okay, so eventually you are modifying, transforming your computational pattern in order to suit what kind of an architecture you have underneath. So the researcher is thinking otherwise. Why not let the neural network remain in their own structure, in their own type, and we change the architecture rather. We don't follow the von Neumann architecture, or we don't apply or force a neural network to modify itself to suit into von Neumann architecture. Other way around. Here we change the architecture itself to suit the neural network. In case of neuromorphic computing, it is much deeper level. What this is at the CMOS level, at the chip level, at the processor level only, we would create a network where the weights and the input voltage and the activator would work on each others, and then the calculations would work. This is much deeper level. We are almost coming up to not architecture level, rather at the processor chip design level. Okay, a transistor level rather, I would say. So that is why, if we are able to succeed in neuromorphic computing, if we are able to succeed by porting, developing a neuromorphic computer where you don't have to change at all the deep learning model, you just need to give it to the processor itself. The processor changes itself to suit and perfectly fit that particular model onto it. Then you see there will be multifold level of performance benefit. And if you as the processor itself to take care of mapping it, it will have a lot of benefit in the programming perspective, also in the power efficiency and performance efficiency. And that is why in latter time many of the premier institutes, IISc and IIT Delhi, they are working upon neuromorphic computing, and government also looking forward to it, because government thinks that AI is one of the technology which can bring changes, positive changes, and society in society. So if in order to do so, they require humongous facilities, computational facilities. Now, if those facilities are consuming so much of power, it is costly affair. So why not to explore alternative architecture, which consumes less power but does the same thing? Now, Cerebras is one of that kind. Here you see, it's not a typical CPU where ALU is there and then they operate. However, it is not completely apart from von Neumann architectures. Here also a compute unit is there, a memory unit is there, but they are called networked compute components. All these blocks are basically some kind of a processor and memory together. Okay, and they are connected with each other. If one of the processor wants to send some data from this block to this block, they don't have to do anything, rather a single clock cycle should transfer the data from here to here. This is the beauty of this architecture. Cerebras is a it utilizes a 2D mesh topology. Okay, and it minimizes the distance and latency between adjacent cores, and that is why it is no more a multi-core architecture. It's a many core architecture, many core network architecture. They have given a lot of emphasis on routings. So there is a routing tables which takes care of mapping the data from one core to another core, or one compute unit to another compute unit. So these architectures are becoming very popular for AI work, because, as you know, if you have a neural network, you need to break them into graph, and that particular graph will be distributing to multiple Cerebras compute unit called CS2 system, and this is again a cluster. So when a deep neural network or large language models, transformer models, uh, goes on executions, this process is called either tuning or fine tuning. So these kind of a training related work requires a computational facility, large computational facility like supercomputers. Now these supercomputers here we call Cerebras systems. There also it is multiple nodes. There would be also again distributions of the data. The middleware takes care of it. So the neural network would be basically converted into connected graphs. That particular graphs will be divided into, and then they will be distributed to different compute node. Now, once you transfer a weight, the further calculations will be taken care of by SwarmX, which is a middleware kind of a thing, and then it will transfer the weights and gradients in reverse, in return, very fast between the systems. The processor is called wafer scale engine. You may Google on. It has 8,50,000 compute cores. Okay, they are called linear algebra compute cores. Each of the systems has 40 GB of high-speed RAM, SRAM they call it, and humongous bandwidth, 20 petabytes per second. They have a bandwidth between the cores and the memory. Don't think that it is between the systems, between the nodes. No, I'm talking about between the cores and the memory itself. That means within the system, 20 petabytes. But yes, in between them also there is high bandwidth connections, 100 GB connections, Ethernet connections between the systems also. So as I was stating, a framework which understand what Cerebras systems looks like. If you give a large language models to it, it will take that particular neural network, break it into a connected graph, and then it will break into an execution plan. How to distribute the data and then execute them, transfer the weights into them, and take back the gradients, and then it will transfer the computations to the facility, the physical facility. This is what the complete cycle of and compute approach on Cerebras systems. Similarly, there was another compute facilities. Our team has worked on Cerebras systems as well as on Graph Core. The another facility is called Graph Core Intelligent Processing Unit. Intelligent processing unit. What it does, you have four processors on a system and a very high cooling and systems, cooling facilities. And then you have this particular chip is a normal processor which looks after offloading the task. Again, the graph block, the distributed graph block to different compute unit. So this is another facility. Let us look into how it looks like. The Intelligent Processing Unit or IPU are basically the cores associated with the memory. So these gray block are the memories and these are the cores. So combined in a combined way, they are called the IPU core. Okay, and multiple such cores would create a tile, and multiple such tiles together is called GC200 IP unit. Okay. So if you look here, they can also again reach out to some communications unit. Here the communications unit. That means this is the routing module or the network which connects all each of the cores with all other cores here. So this is called IPU exchange in terms, and very powerful memory exchanger, or I would call network between cores. So this is only responsible to transfer some data from one core to another. If you have to transfer data from this particular systems to another unit, in that situation you will be using IPU link. If you want to IPU link, okay. So let me give you a. So if you want to transfer the data from this unit to this unit, you will be using IPU link, okay. But if you want to transfer the data from this unit to another unit, then you will be using called PCI link, high bandwidth PCI link anyway. And the programming model is called bulk synchronous programming paradigms. What it simply does is very simple. Let me see. You have a synchronizations block, you have computation block, you have exchange block, and waiting block. What it simply says, synchronizations means a barrier point. Computations means in this particular time, some computations are happening on each of the cores, embracingly parallel, not no communications are happening, and then the communications are happening. Exchange phase, and once it is done, it will wait for some time in order to ensure that all the cores on IPU system has completed their calculation. Once that is done, then again the synchronization phase will appear like this, synchronization phase, and the cycle will continue. It is like fetch, decode, execute, and write back. So this programming model earlier in 2000, it was very popular and coming up, and people thought that this will replace generic programming, parallel programming paradigms, which did not happen. But yes, it is also again coming up in other way for specific systems like Cerebras and IPU, Samba Nova, etc. So in case of if you map the concept, here also it is true that initially it is fetch. That means you are fetching the data from one node to another node, and then you'll be decoding the data, what to do with it. Once the calculations are happening or executions happens, then you will be right back to some units. So that is how the bulk synchronous programming model, which also operates on this particular approach: synchronizations, computations, exchange, and waiting. These particular cycles of execution stage repeats itself throughout in the calculation phase, and indirectly maps with what happens in a neural network, and that is why they are quite friendly on architecture like IPU as well as on Cerebras. So this is what recent things are happening, and we believe in future more such processors would come because they are power efficient, they are more friendly to the graph computations, and that is why they would become more prominent AI compute engine rather than a normal CPU. And in current time, if you see more than CPU, the GPUs are more important for artificial intelligence. In future, we believe this kind of architecture should become more prominent. So there is a shift happening in the trend. We are slowly shifting from generic purpose computations, CPU computations, to specific computations to network oriented computations. And then the last part of it is quantum computing. In quantum computing, we believe, I was talking about HPC perspective, that we believe there are some phenomena. Currently, we are simulating through digital algebra, digital computations, which is not very efficient time wise, power wise, and money wise. Rather, we would simulate them on quantum systems, and that is why we have came up with a quantum computing concept, hybrid HPC quantum computing concept. In quantum computing, there are many players are there at this point of a time who build the processor. Whereas we are looking forward to at the middleware portions, we plan to have the processes from different players. Many other components like dilution refrigerator, control unit, wherein calibration software stacks. We are planning to have it either indigenously built from other parties, and we are planning to build a reference facility. So these are all different components, and at this point of time, different techniques are also available. Superconducting technique, many other techniques are available for realizing a qubit. These are different components of your quantum computing systems or quantum computing processors connections. Um, this is a control unit again. This control unit is developed by CDI Bangalore, and they are working very aggressively on building a scalable version of this so that it can become the indigenous quantum computing control unit. So we plan to build a facility where we would be doing a lot of R&D ourselves. We will be connecting to various industries because we cannot do everything by our own. So collaborations is important. We'll have international collaborations, and this facility would be called as a reference facility, which would be also again used for testing, validations, benchmarking purpose. That is how we plan to build hybrid computing systems where quantum systems and HPC facility would be connected together. Uh, Variational quantum algorithm is one of the first candidates that we plan to look into. This algorithm is basically the part of a software like Quantum Espresso. Quantum Espresso is a scientific simulation software, but the kernel of it is DFT, and this DFT's main algorithm is VQE. So we plan to use VQE as the first candidate for exploring hybrid computing facility. We believe that once HPC is connected with quantum systems, and we are able to successfully create a middleware for both of them to work collaboratively, we believe the quantum advantage we will be able to realize. How we are planning to do this is a block diagram of it, where the network facilities or network interconnect of an HPC facility would again be connected to the quantum facilities. The middleware, the OS would be recognizing that another accelerator has been connected for our scientific simulations. So wherever there is a compute intensive part which is capable of doing the executions in a quantum way, would be transferred back to the quantum systems, and the result will be taken back to the traditional computing facilities. This is a block diagram which telling that how the workflow is going to work, how the CPU workload, and then from CPU task to CPU task. This is how it happens in a parallel programming. But on the other hand, if it is a hybrid workload, quantum workload, CPU tasks are divided into different kind of CPU task as well as quantum task. So this is and then both of them would interact with each other as a program called ASA functions, and that is how interactions will happen. The executions will complete as a final CPU task, and a traditional way we will be able to investigate the result. This is the facility we want to create by ourselves. This I have explained in my keynote talk, and this is one of the POC we have developed. We took the help of NPI programming paradigms, where one of the compute node were considered as a quantum simulator, and that simulator were capable of connecting either simulate the task with it, or they were through cloud were able to connect to IBM cluster quantum system or many other quantum systems. So that means in traditional workload, if there is a function which is a classical, it will get executed on this node. But if there is a quantum functions after these classical functions, these functions will call this will basically get uploaded through network through this interface to this particular block, and it will connect either to simulator or cloud. Through cloud it will connect to the quantum systems, yeah, and execute that simulations and transfer back the result to here. Once this is finalized, then the functions 3 which is depend on the output of quantum functions quantum q2, it will start executing. So this is one of the way of realizing how an hybrid HPCand quantum facility may work. It is very simple to explain, but yeah, quite a challenging part in realization. We have developed a POC of it, but we are working for a full-fledged facility of such. When we are thinking of having a hybrid facilities, these are the different areas, research areas we have to put effort into, including integration, testing, and validations. But the major part where I am interested in runtime development. So, to conclude, I started with explaining all these to you. Now I'm giving you a programmatic mapping where we say scientific simulations. For all scientific simulations, major scientific simulations, HPC and grid computing were the computational field, basically the computational infrastructure. Large scale distributed computing, for that, grid computing and cloud computing was the play field. Basically, they are the infrastructure for that. For graph computing, AIDL, and neuromorphic computing, HPC and cloud computing is the current infrastructure, but yes, more specific infrastructure is going to come in future. High throughput For high throughput computing, yeah, big data clusters and cloud computing is the most preferred. For quantum computing and hybrid HPC we'll be developing a hybrid HPC reference facility for that purpose. That is our aim. So this brings me to the end of my presentations, and yeah, I think I'm 7 minutes over the time. So if there is a quick questions, I would love to take it. Otherwise, Madam, over to you.
Participants, please unmute yourself and ask the question. Sir, there is one question in chat box from Devendra Maharana. What is the difference between YAN and SDFS? It is required to schedule any big data job tasks in YAN or SDFS.
Okay, that's a great question actually. Yarn is a scheduler. It's a meta scheduler. That means it's responsible for scheduling the task to different compute unit. So, like suppose I tell you that you manage a big task, then you will be also uploading the task to your subordinates. So Yarn does that. Yarn is preferred in Kubernetes cluster and in big data cluster, whereas in HPC cluster there is a scheduler called Slum, simple Linux utility manager, Slum. Okay, so that is also a meta scheduler. Whereas HDFS is a file system which supports parallel access and this parallel distributed access, HDFS. Next question, please.
In, unmute yourself and ask the questions. Participants, Please unmute yourself and ask the questions.
Ma'am, there is a question from Bhagati sir in chat box.
Okay. Yeah. It is required GP if working on CSV files. Well, so CSV files, basically text files, uh, it depends on how large the CSV file itself. Okay, it may not require a CSV file, but if you have a collection of CSV files, if you have thousand of CSV files to process, then you would be requiring a GPU, and it is better to have a GPU in that case because CPU would not be sufficient to. It will take lot of time. So you may use a GPU if you have a lot of collections of CSV files, not a single one or two CSV files. Okay. I think there is no other question.
Okay. Okay, I think there is no other question, right?
Yeah.
So just a minute, sir. I will share the screen.
Yeah.
It is visible, sir.
Yes, sir. Yes.
Yes, ma'am.
On behalf of everyone here, I extend our deepest gratitude to Mr. Samrit Kumar Metti sir for his insight into the future trends in computing. His ability to explore the possibilities of these advancing fields has inspired us to envision the next era of innovations and progress. Sir, please accept our virtual token of appreciation. Thank you, sir.
Thank you, sir.
We would also like to acknowledge and express our thanks to all the attendees. Your presence has made these sessions all the more meaningful and memorable. Attendance and feedback links are given in the chat box. I request all the participants to go through it.
Okay. Thank you then. Have a good day. May I
Thank you, sir.
disconnect now?
Yes, sir. Please. Thank you,
Thank
sir.
you, sir. Thanks a lot for joining.
Thank you. Thank you. Thank you, ma'am.